Hello again, grade 11 chemistry students. Today what we're learning about is quantities and chemical reactions. We are focusing on learning the empirical formula today and also the molecular formula. You already know the law of definite proportions, and you know that it relates to something called the percentage composition of a compound. So once we know the percentage composition of a compound, what we're going to do is we're going to turn it into something called the empirical formula, and then finally we're going to turn it into the molecular formula. This is what I'm going to show you how to do today. Okay, you should already know what the molecular formula already is. It's the actual amount of atoms in a molecule. So here we have some chemicals. I'm going to write down the molecular formulas for each one. So here we have the actual amount of atoms in this column here. You can see all the formulas here. Well, let's actually write down the empirical formula now. I haven't explained what it is. I want you to try and figure out what it is. Now, when we look at the empirical formula, we see that some have changed. Glucose, hydrogen peroxide, benzene changed, aniline did not change, and water did not change. Now, what could the empirical formula be relative to the molecular formula? Well, maybe this will help. If you haven't figured it out, let me show you the lowest ratios of each one. Well, if we look, we can see that the lowest ratio actually is what represents the empirical formula. And this explains why some did not change. For example, aniline did not change, and water did not change. And the reason why is because they're already in their lowest ratio. If you have C6H12O6, each one can be divided by 6, and that turns it into a 1 to 2 to 1 ratio. So the empirical formula is the lowest ratio of elements to one another. Now, it doesn't necessarily, the ratio cannot tell us what the chemical is. The empirical formula for acetylene, you'll notice, is exactly the same as benzene, but they are very different chemicals. The molecular formula makes all the difference in the world, so the empirical formula is not always the most informative thing in the world because many different compounds share the same empirical formula, have different molecular formulas, and so therefore different properties. So molecular formulas have different properties, whereas empirical formula is just the lowest ratio. We are going to find that, though, is that when we know the empirical formula and the molar mass, we're able to take our empirical formula and turn it into the molecular formula. So let's write this down. What's the difference between empirical versus molecular formula? Well, the answer is the molecular formula is the actual amount of atoms. The empirical formula is just the lowest ratio of atoms. And we always say that ionic compounds are always an empirical formula. Let me explain. This is a picture of salt. Now, if we were going to write the formula of this, you may be tempted to say, well, let me count them all. Looks like I might have 1,000. I'm not sure, sir, but I think that's right. So this is the formula, Na1000 to Cl1000. Well, that's complete garbage because that doesn't make sense. Remember, it's positive and negative ions, so we always write the empirical formula, okay, for ionic compounds. Whereas H2O, it's always in its lowest form, or so not. It's not always in its lowest form, but empirical formula. There's no such thing as molecular formula for ionic compounds. Okay, so here we have a problem. It says determine the empirical formula, and what it's given us is percentages, compositions of our compound. So we know 85.6% of our compound is carbon and 14.4% of it's hydrogen, and it's asking us to turn it into the empirical formula. Well, there's some steps that we can do here that will always help us do this, and we need to write these down. Step one is that we assume we have 100 grams. Okay, so if I assume I have 100 grams, what's 85.6% of 100 grams? Well, the answer is 85.6 grams. So all we're doing is we're taking our percentages and we're turning them to grams by assuming 100 grams. So then we also have another mass of, so that's my mass of carbon. My mass of hydrogen is going to be 14.4 grams of hydrogen. Now, the reason why we're going to do this is we're going to try and convert this to moles next. So we convert the grams to moles because when we find a formula, remember the formula, whatever it is, it's a quantity. It's an amount of atoms in a ratio to one another. So we have to take our mass and turn it into a form of a quantity, and it's very easy for us to take grams and turn them to moles, which is a quantity as well. Okay, so we know that moles is equal to mass divided by molar mass. So I'm going to do this calculation for carbon, then I'm going to do it for hydrogen. Okay, so I've taken my mass, 85.6 grams of carbon. You notice I have subscript written right here. Well, that just, little C there helps me keep track of what I'm talking about. You can put the C after, and that's fine too. I don't mind that, but if you put it in subscript, you're really keeping track of it. Now I'm dividing it by the molar mass of carbon. And I'm also taking the mass of hydrogen and dividing by the molar mass of hydrogen. Now notice this is not diatomic because we have in our compound, it's only diatomic when it's on its own. So I'm not going to use the molar mass times 2 because this is singular hydrogen. This is not diatomic when it's in a compound. Let's look at our answers here. Okay, so now we've successfully converted our carbon from grams, from percentages to grams to moles, which is a quantity, and we're comparing the two moles. So we have 7.13 moles of carbon and 14.26 moles of hydrogen. Now, the question is what is the ratio between these two chemicals, carbon to hydrogen? What's the lowest ratio? You should already be able to tell what it is. Well, if you don't, let me show you the third step. The third step says is find the ratio by dividing by the smaller mole value. So we're going to divide 7.13 divided by itself, and which is going to be 1. 7.13 divided by 7.13 is 1. And 14.26 moles divided by 7.13, which you should see is 2. So our ratio is going to be 1 to 2. So we've written down our moles. We divide by the smaller moles. And again, the ratio is for every 1 mole of carbon, there is 2 moles, or sorry, you know what? The moles even cancel out there. For every 1 carbon, there is 2 hydrogen. So therefore, the empirical formula is CH2. That's the lowest ratio. Now let's think of some possible molecular formulas for this. Well, it could be CH2. That's one possibility. Molecular formula is the actual amount. Remember, empirical formula is the lowest ratio. Well, it also could be C2H2, or sorry, C2H4, or C3H6, or C4H8. What do these all share in common? Well, they all have the ratio of CH2. This is the molecular formula. This is the empirical formula. How do we take our empirical formula and turn it into a molecular formula? That's our next step. So to find the molecular formula, well, let's ask the question, why do we have to find it in the first place? Why can't we just live with the empirical formula? Why is the empirical formula not always the most relevant piece of information about a compound? Well, the answer is you should know already, because the empirical formula could represent various molecular compounds. It could be lots of different compounds share that ratio. To answer the question of what the actual molecular formula is, we need to know the molar mass, or the molecular mass of a compound, and we do that using a mass spectrometer. And what a mass spectrometer is all you have to know is it's an instrumentation. It's very expensive. You put it on, you put your sample on, and it's capable of is telling you the molar mass. So we're going to use the molar mass to determine the molecular formula from the empirical formula. So you just have to know the mass spectrometer is how we find the molar mass. Enables us to find the molecular formula from the empirical formula. So chemists use a mass spectrometer to determine the molar mass of a compound. Okay? Knowing the molar knowing the molar mass of the empirical formula and the molar mass of the molecular formula allows us to figure out the molecular formula. So let me show you what I mean by that. We have an example where we have an empirical formula of CH2O. It's ribose, okay? And we used a mass spectrometer. We found out the molar mass of the molecular formula is 150 grams per mole. What is the molecular formula? Well, let me show you how this information is useful. Okay, so our empirical formula is CH2O. Can you guys think of some possible molecular formulas? Well, if you thought CH2O is a possibility, that's correct. Well, it also could be C2H4O2, or it could be C3H6O3. Where did I get those numbers from? Well, basically, I just multiplied them by 3, multiplied them by 2, and just kept it the same by multiplying by 1. Now, why does it matter? Well, the answer why it matters is because we're also going to multiply the molar masses by these numbers as well. So if we know the difference in the molar mass of this compared to this, we will know what number we have to multiply our empirical formula by. So let me show you what I mean. Let's find the molar mass of our empirical first. So I'll just write it down like this. That is 1 carbon, 2 hydrogens, and 1 oxygen. So when we calculate the molar mass of empirical, we determine it to be 30.03 grams per mole. Let's compare that to the molar mass of our molecular. And we find out it's just from our question. It is 150 grams per mole. Well, just look at that. What's the difference on average between those two numbers? If we divide our molar mass of our molecular, and you should always write this down because this is how you do it all the time, divided by the molar mass of the empirical, we find out that it's approximately 5 times larger. As a matter of fact, it's almost exactly 5 times larger. So therefore, our empirical formula, our molecular formula will be CH2O, but since it's 5 times heavier, we are going to multiply each one of these numbers, these subscripts, times 5 to make it 5 times heavier. So therefore, our molecular is going to be equal to C5H10O5. And that is our molecular formula of this compound because it is 5 times heavier. So to summarize, all we do is we're given the molar mass of the molecular compound in the equation. We find the molar mass of our empirical, we divide it into it, we find out how many times heavier it is, and then we multiply that number into our empirical formula to get the molecular formula, and that is it. If there's any questions, let me know. I'm going to give you one question I'd like you to try for tomorrow. Okay, so first thing I'd like you to do is you are going to find the empirical formula, okay, for giving the steps that I told you earlier. Assume 100 grams, then take your mass, turn it to moles, then divide by the smallest moles, okay? And that should give you a ratio. Then what you're going to do to find the molecular is you're going to divide the molar mass of the molecular, of the molecular divided by the molar mass of the empirical. You'll get a value and multiply this value by the empirical formula, and you will get the molecular formula. Those are the steps that you need to take to answer this question. Thanks for listening, and I hope you enjoyed your day.